Little reminder, continuing from last day, make sure you write the magnetic forces test. It's on lots of right-hand rule stuff and bending charges into circles and that kind of a thing. For each instance below, it says find the induced voltage, the net voltage, the current magnetic. You know what? It's the same picture, except in one we're standing still, in another one we have a velocity. So I'm going to kind of do each one side by side, I think. I'm going to draw a little line down the middle. I'm going to start out with the induced voltage. Why for the first situation? Well, what is the induced voltage for the first situation if I'm standing still? We said induced voltage was equal to the magnetic field times the length times the speed, and since the speed is 0, 0. Here, the induced voltage is going to be BLV, magnetic field 0.35, length of wire 4.1, the diagram says, speed 8. What will the induced voltage be? What will the induced voltage be? Come on. 0.35 times 4.1 times 8. 11.5? Is that right? Okay. What does B want me to find? Oh, the net voltage. What's my source voltage? 320. So I guess in the first situation, the net voltage is just going to be 320 volts. I guess in the second situation, the net voltage is going to be 320 volts from the source minus 11.48, 11.5, but I think it was 48 on my calculator, wasn't it? It's going to be 309 volts. Heck, I'll even go 308.5. I'll go to 4 sig figs just this once. Is there still a positive voltage going through this bar? Yeah, so it's going to continue to speed up. But as it speeds up, as this gets bigger, what's going to happen to my induced voltage? Bigger, smaller, or stays the same? Bigger. What's going to happen to my net voltage? Bigger, smaller, stays the same? Okay? This is a situation, those of you that are in calculus, this is a situation where the acceleration would have a derivative. The acceleration has a changing rate. Which we've avoided all of physics 12. All of our accelerations have been constant. Not here, because your rate of change of speed is changing. C says, find the current. So current is voltage divided by resistance. Current is voltage divided by resistance. Total voltage, 320, divided by 8.5. Total voltage, 308.5. divided by 8.5. Minus Mr. Dueck, divided by 8.5. You'd have 37.6 amps. And here you'd have 36.3 amps. What's the last thing it wanted me to find? Net force? Magnetic force. So C, not net force, but the magnetic force. Well, the force from a magnet on a wire, the force from a magnet on a... What is the force from a magnet on a wire? Bill, which is on your last... It's on your magnetic forces test. This is one you need to know already. Bill, which is going to be, what did we say the magnetic field was? 0.35. Here the current is 37.6. Length is 4.1 meters. This is going to be 0.35. Here the current is 36.3. Length is 4.1 meters. 0.35 times 37.6 times 4.1. 54 newtons. 0.35 times 36.3 times 4.1. 52 newtons. So once it starts to move, what did you notice happened to the force? Bigger, smaller, or stays the same? Smaller. As it speeds up, what's going to happen to the force? Bigger, smaller, or stays the same? Smaller. And since F equals ma, what's going to happen to, because the mass isn't changing, what's going to happen to the acceleration? Bigger, smaller, or stays the same? It's also going to get smaller. This is why technically I can't look at the, a great question would be find the acceleration, but if we solved for an acceleration, we would actually get an equation, not an answer. It would be a derivative. A pretty cool one. Derivative. Okay? So adding to the homework a little bit, can add, try 6. And 8. Okay? But now we want to move on, and I'm sorry I can't pause, but I got to get lesson 2 done. So thankfully I can pause the video. So let's put this all together. Lesson 2, instead of inducing voltage in a wire, let's induce it in a coil of wires. The generator. Here is a very simple prototype of a generator, of an electric generator. Faraday said, look, if motion can induce a magnetic field, maybe a current can create motion, maybe motion can create current. If current can create motion, motion can create current. So here was his setup. You'll notice we have a North Pole magnet right here, South Pole magnet right here. So the magnetic field is pointing to the right. Okay? We are going to spin this armature, this single coil of wires. Normally you'd have a whole, like thousands of coils, but we're looking at one single one. We're going to spin it. How? Hey, hook it up to a water wheel, say, or a hydroelectric dam, or windmill, or, hey, oh, is that why like stuff that generates electricity tends to move in a circle? Yes! Yes. Okay? And simplest case, let's look at one single solitary positive charge sitting right there in the middle of that wire right there. Okay? If you look on the very, very end of the diagram, we're rotating this clockwise, which means this positive charge on the right-hand side of the wire is moving downwards. What direction is the magnetic field? To the, look at the picture, to the right. So if this charge is moving downwards and the magnetic field is to the right, on the right-hand side of this wire, which way will the charge feel a force out of the page towards us? On the right-hand side of this piece of wire, the charge is going to feel a force that way. In fact, the current on the right-hand side will flow that way. On the left-hand side, and it's screened out by the magnet, but you can imagine there's a little positive charge sitting right there, moving up. Magnetic field still pointing to the right. Oh, on the left-hand side, the current would flow. In fact, what we have is a current going. Now, if we want direct current, we can use that same split ring commutator brushes system to keep the current always going in the same direction. Or if we ditch that, we get lovely alternating current, which is easy to create, and it's one of the reasons why what comes out of your plugs is alternating current. Even for direct current devices, we still go with an alternating current source. It's so easy to create. So the generator was invented by Michael Faraday, one of my nerd heroes. The previous figure shows a simple hand-operated generator with a coil consisting of only one turn. It's exactly what was going on with my flashlight, which I put where? Here, flashlight. Where did I put it? Somewhere down. Sorry? Cal, remember what I put it after where I put it? Let me first of all do this so I'm not irritating people. So, generators. We're going to get to this setup in a second, but I want you to look here. What about when the wire is at the very top? Now, at the very top, instead of moving down right here, at the very top, the wire is moving to the right. Which way is the magnetic field? Also pointing to the right. So when the wire is vertical, no charge will be induced. When the wire is horizontal, maximum current, I said charge, current, maximum voltage will be induced. In other words, if we look at this picture here, when it's vertical, a voltmeter would read 0. When it's at a 90-degree angle, you'll get a maximum induced voltage. Then the voltmeter would go back to 0. Then you'd get a maximum negative induced voltage. In fact, you're starting to see alternating current appear. Is that okay, Elijah? Yeah, good, shut up. Okay? So, when the coil is horizontal, the segments in which an EMF can be induced are perpendicular to the lines of force through which they're moving, and the induced EMF is at its maximum or peak voltage. And when it's parallel, you get nothing. Blah, 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 blah. Here's the question. How can we combine induced voltage in a wire and induced voltage in a loop of spinning wire? How can we combine them? Right now we have E equals BLV, which works great when I'm moving a wire at a constant speed, but when I'm spinning. Figured out where we are? We've turned the page. Okay. Consider the following example. We have a rectangular loop of wire, and it's being moved to the right. Someone is dragging it. And it's being moved perpendicularly to a magnetic field. So which way is the magnetic field? Out of the page towards us. See the dots? Where will there be an induced current? Well, why can I go like this? Will there be an induced current at location A or location F? Because there's no magnetic field. Okay. Let's look at location C. I think, first of all, location C and location D really are the same. They both are totally inside the magnetic field. They're both moving to the right. So let's look at, first of all, we can, don't write this down, we can ignore that and that because these are moving parallel to the direction of the length, so we're not going to have any voltage induced there. Let's look at a positive charge right there and a positive charge right there. Which way is this front positive charge moving? To the right. So point your fingers, your thumb, sorry, to the right. Which way is the magnetic field? Out of the page. This charge is going to get forced down. What about the back, a charge sitting in this back chunk, the rear chunk of wire? Which way is he moving? To the right. Which way is the magnetic field? Out of the page. Which way will he feel a force? Or she feel a force? It feel a force. So it looks like I have this. Charge is getting forced down on the left-hand side. Charge is getting forced down on the right-hand side. What's my net voltage here? 0. you're not going to get any voltage at location C and location D. What about at location B, where half the coil is in the magnetic field, but half isn't? Again, let's look at the charge here and the charge here. Well, first of all, this guy's not going to feel any force whatsoever because he's not even in the field. But where will that right-hand charge feel a force? Down. So you're going to get a clockwise current at location B. See it, Callum? What about when you exit the magnetic field, when half of you is out the magnetic field and half of you is in? Well, again, I can look at a little charge right there and a little charge right there. But again, I would say, you know what? That's outside the magnetic field. It's not going to feel a force. Which way will that leftmost charge feel a force? Down. In fact, now the current is going not clockwise, but which way? Counterclockwise. Alternating current. Oh, okay, starting to see why this is why we deal with it. So it looks like the two places that you get an induced current in a coil, not on a single wire, but in a coil, are Curtis, you okay with a little thought experiment? Yeah. And then Faraday said, why? Why is, I mean, I understand from my thought experiment, Faraday thought, and he said, there has to be some way that I can unite a single wire with the physics of a coil. So it says why, we've kind of explained it. We're going to go to the next page. Here was where we say Faraday was brilliant. He said that, I know what induces a voltage and therefore a current. It's induced in a coil of wire when the area of the coil that was exposed to the magnetic field changes. He said, in this situation, you have zero area exposed to the magnetic field, zero area exposed to the magnetic field, no voltage. In C and D, he said, you have all of the area exposed to the magnetic field, it's not changing, no voltage. He said, here, you have the area that's exposed to the magnetic field. Give me a second here. What's happening here is the amount of area is increasing. That's going to induce a current. And here, the amount of area through which the magnetic field is flowing is decreasing. That's going to induce a current. And this leads us to the concept of magnetic flux. Magnetic flux is the number of lines of magnetic field passing through an area. Magnetic flux is the number of lines of magnetic field passing through an area. Let me show you what I mean. Okay? We're going to use my projector as a flashlight, but instead of light, imagine it's magnetic field beams. And I want to maximize the amount of flux, the amount of light going through this ring of tape. How much light is going through this ring of tape right now? It's meant to be an obvious, easy question. 0. What's happening to the flux passing through the tape as I rotate it? Increasing, decreasing, or staying the same? See it? This is maximum. And this is 0 again. So Faraday said, one way that you can change the amount of magnetic flux, the number of magnetic field lines, just as though I had a flashlight, he said, I'm going to think about a magnet, is I can change my area. This is why most of our generators spin. You're changing your area. There's another way I can get more lines of light. Look up, look up, look up. What's happening to the number of the amount of light passing through this piece of tape as I move closer and closer and closer to the bulb? Increasing, decreasing, or staying the same? Increasing. Right? Increasing. decreasing. Still light going through, but nowhere near as much. In fact, there I got maximum flux. Magnetic flux is the number of lines of magnetic field that pass through a particular area, and there's two ways to increase flux: increase the area or move closer, strengthen the field. It's two ways to decrease flux: decrease the area or weaken the field by moving away. The symbol for flux, a TIE fighter on its side. Although that's technically the symbol, traditionally we stopped doing the little wings on top and bottom. It's often just written like that. The units, well, I got to be honest, there's all types of flux. There's electric flux, there's photovoltaic, light flux, but we're looking at magnetic flux. The generic units for any flux is actually lines. How many lines are passing through the area? But the units for magnetic flux is your last unit of the year. Weber's, symbol, capital W, lowercase b. Can't use just capital W because that's watts. Weber's. How do we calculate flux? Faraday said, you know what? It's the strength of the magnetic field times the area that's exposed to the magnetic field, but these two need to be at right angles to each other. If they aren't at right angles to each other, if they're parallel, how much flux is going through this roll of tape? 0. Maximum. And this is why we get alternating current from our plugs, because in a generator, when you have the coil spinning, what you're really going is from maximum voltage, less, 0, more, but now this coil has spun around, negative, max, less, 0, positive, max. This is why we get alternating current. And those of you that are doing Math 12, you'll recognize a trig function, a sine wave, or a cosine wave. So, for each orientation of the spinning loop shown below, what can you tell me about the amount of flux passing through the loop? Which one of those, A, B, or C, has no flux passing through the loop? C. Which one of these has the maximum flux passing through it? In situation B, is the flux increasing or decreasing? I can't tell unless you tell me which way this is spinning. So let's add an arrow like this, and let's say the spin is that way. So if the spin is that way, is my flux increasing or decreasing? Decreasing. What if the spin was the other way? Increasing. So I'm going to say here, flux decreasing. Okay. So, describe whether the flux is increasing, decreasing, or constant in each case below. And let's make a little note here. Magnetic flux is equal to B times the perpendicular area. That equation is on your formula sheet, but I don't think the perpendicular symbols are. But I think it does say flux equals BA. Flux gives you a bad attitude, BA. Okay. What do you think, situation A? If I increase the magnetic field, what do you happen? Is the flux, what do you think happens? Flux constant, increasing, or decreasing? If this bulb gets brighter, will more lines of light flow through it, less lines of light flow through this, or the same amount? Okay, flux is increasing here. What if the magnetic field decreases? By the way, we did kind of a half loop. You got to kind of imagine the other loop behind, but right, you can figure out from the picture. What happens to the flux here? What about situation C? The amount of magnetic field lines passing through this loop, do they increase, decrease, or stay the same? So does the flux increase, decrease, or stay the same? What about situation D? Now, here was Faraday's brilliance. We've seen this picture before, and here's what Faraday said. He said, there is an area that's increasing. Which area? The area behind the bar. As this bar moves to the right, what happens to the area? I never would have thought of that in a million years. But this is how he was able to link flux, area, a coil, and this wire. What about situation E? Okay, we got a coil of wires. Is the area of the coil changing? Is the magnetic field exposure changing? Okay. What about situation F? Is the area of the coil changing? No. But you know what? We're moving the magnet closer. When you move a magnet closer, what happens to the magnetic field strength at your location? If a magnet's moving closer to you, are you feeling the magnetic field stronger, weaker, or the same? So in this case, magnetic field is increasing, which means the flux is increasing. Ah, what if we spin the coil? Michael, we're going from maximum flux right now to, once it ends up like this, we'll have a flux of 0. So yeah, I think spinning the coil causes the flux to decrease. What if we squeeze the loop, shrinking the area? That will also decrease the flux. We're not changing magnetic field, but we're changing the area. Ooh. What if I have a coil of wires here, not touching anything else, but I have an increasing current? Let's draw in the current. It's going to the left. Hey, this is a good review of the right-hand rule for a current-carrying wire. Point your thumbs to the right in the direction of the current. Now, we don't want to know what's happening to the wire. We want to know what's happening to the coil. So we want to know what magnetic field this wire is creating. Curl your fingers. That's the direction of the magnetic field. You know what? Right here, I have a magnetic field coming out of the page. As current increases, what do you think happens to the magnetic field strength? Increases, decreases, or stays the same? Increases. So what do you think happens to the flux? In this case here, what that means is, in that coil of wires, you would be inducing a current without touching the first wire. This is how the cordless charging systems of your future cell phones will work. Okay. Anybody have a cell phone that you just lay down on a pad to charge it up? You do? And probably 2 generations of phones, that'll be the standard. So we can now give you a general rule. Previously we said an induced voltage was created when we changed the field or the orientation or the area. We can now summarize that. You know what? Induced voltage is created if the flux changes. And what's the flux, Kelly? The number of magnetic field lines passing through the area, calculated by magnetic field times area. In fact, Faraday did a bunch of experiments, and he found that, oh, if I want to double the voltage, have 2 coils of wire. If I want to 100 times the voltage, have 100 coils of wire. He found that the voltage varied directly with the number of loops of wire. That's the bottom one. He also found it varied directly with the change in flux. The faster he changed the flux, the more he changed the flux, the bigger the voltage. He found it varied inversely with time. A faster change led to more volts. He found Faraday's law. Faraday's law. Underline Faraday's law. In fact, really, I should have put a box around this, because this is big equation number 2. And it says this: the induced voltage when you're spinning a coil is equal to, leave a space, N change in flux over change in time. And in the space, put a negative. Where N is the number of coils of wire. This is the change in flux. What's change in anything? Final minus initial. Okay. And delta T is, hey, that hasn't changed. Change in time. Ashley, why negative? Can I tell you next class? Can I tell you next class? So, next example. I like this question. I like this question. I like this question. A circular loop of wire. Can you all underline the word Seriously? A circular loop of wire of radius 2.5 centimeters is in a magnetic field of 0.4 teslas. If the loop is removed from the field in a time of 0.05 seconds, what's the averaged induced EMF? What do they want me to find? What do they want me to find? Don't write this next bit down. For a single straight wire, I use BLV. For a loop or a coil of wire, I use negative N change in flux over change in time. And I'm going to defic. Alex, I'm going to list my data. What's N? N is the number of coils of wire. How many coils of wire do we have this time? This is why I asked you to underline that first word. 1. A lot of kids miss that. Okay? When it's a number and I tell you it's easy, but if it says for some reason they miss that. So in this case, N is 1. The other easy one to get is the change in time. What's the change in time here? 0.05. The third thing I need to find is the change in flux. What's change in anything? Final minus initial. Now remember, Elijah, I said flux is the number of magnetic field lines. Look at the picture. Folks, what's the final flux? How many magnetic field lines are going through the area in the final part? It's meant to be obvious. You see it? 0, right? So, you know what? 0 minus. What's the initial flux? Well, I said flux was magnetic field times area. Sometimes they'll give you the area, or sometimes they'll tell you the shape and give you enough information to find the area. In this case, they've given me the shape, circle. And what else did the question tell me? Radius. What's the area of a circle? And yes, it's actually on your formula sheet if you don't have it memorized. And you don't have it memorized? Okay, circumference is 2 pi r. Area is pi r squared. 2 pi r squared is part of a cylinder. Well, anyways, it's not. Okay? So this is going to be magnetic field times 2 pi r squared. 0 minus, what did they say the magnetic field was? I hope they told me. I think they told me. Okay. By the way, eventually, instead of giving you the magnetic field, I'll tell you the solenoid that's creating the magnetic field, and then you can use the B equals N-I over L, mu naught, that one, to find the magnetic field, and you start putting everything together. But for now, so what did they say it was?
It's just pi r squared.
Oh, I did what, oh man, Dueck. Thank you. He's got my brain going on it. Sorry, Nate, what was the magnetic field? 0.4? Yeah. And then times pi. And then please tell me they told me the radius. I hope they did. Meters, please. 0.025. So I think the change in flux is going to be 0 minus 0.4 times pi times 0.025 squared. I get negative 7.854 times 10 to negative 4? No, yeah? Units. What were our new units for flux? Webers. So this is going to get plugged into here. I'm going to get the induced voltage is going to be negative 1, negative 7.85 times 10 to the negative 4 divided by 0.05. The induced EMF, the induced voltage is going to be negative 1 times that answer divided by 0.05. And I get a pretty small induced voltage, 1.6 times 10 to the negative 2 volts. What if I wanted 16 volts? Just add, I think, 1,000 wires. Let me see. 16 divided by this answer. Add, if I had 1,018 wires, there, I got 16 volts. Which is actually kind of nice. What this means is I have a very customizable generator. Whatever voltage I seem to need for whatever, I could just add more coils of wire in this system. This is a terrible example, though. This is moving it out of the magnetic field. Must be a better way. How many more have I got here? Good. Nearly there. A square coil, a square coil of wires 5 centimeters on the side has 100 turns. It lies perpendicular to a magnetic field of strength 0.02 teslas. If it's rotated through 90 degrees, I guess if initially it's perpendicular to the field and it's rotated through 90 degrees, can you tell me what the final flux must be? Okay, good. What's the average induced EMF? So we're talking about a coil of wires, so the induced EMF is negative N change in flux over change in time. By the way, you may notice, although I had a negative, I did get a positive answer, and that was because my final flux was 0, and I got a minus in the question. Kind of convenient. What's N in this question? 100 turns. What's the time in this question? Really? That distracting? It's music. Focus. What's the time in this question? Can I just go 0.002 because that's less writing? The one you'll spend the most time finding, change in flux. And I don't take shortcuts there. So I'm going to write out change in flux is going to be final minus initial. What did we say the final flux was? Since it's rotated 90 degrees, 0 minus BA. Magnetic field, 0.02. Oh, negative. 0 minus. A. What shape?
Square.
What's the area of a square? Well, a square is a rectangle. What's the area of a rectangle? Base times height or length times width. But what makes a square? The fact that the base and the height, or the length and the width, are the same. So you know what? I think it's just going to be 0.05 squared. I get negative 5 times 10 to negative 5. Webers. Now I'm into the plug and chug range. Let's see. Negative 100. Negative 5 times 10 to the negative 5. All divided by 0.002. Again, you'll notice in this case, wonderfully, I get a minus minus, which is a plus. Negative 100 times answer button divided by 0.002. Hey, this is a little better. 2.5 volts. The induced voltage will be 2.5 volts. Put your pencils down, look up. Okay, so here's my magnetic field. Okay, here is my induced current, my coil. How can I change the flux? One way is to show field, sure. Pick up coil. There we go. One way is to move the magnet closer or further away, because by doing that, can you see the light bulb start to glow briefly? By doing that, I'm changing the amount of magnetic field. Is there a field meter? I'm changing the amount of flux, In fact, I can even, instead of having a light bulb, give you a voltmeter. Why does the voltage change direction? What do you think about that? Okay. Do it faster, bigger voltage. I'm not changing the area, but by moving closer, I'm increasing the magnetic field. And again, as soon as I stop, what happens to the voltage? This is what scientists hadn't noticed. They had been doing the experiment, and they had looked at their final result, and nothing. Faraday was the one who noticed, wait a minute, the needle was moving while I was moving. Brilliant. No one had caught that for about 10 years. He was the one who, wait a minute, it did move. Maybe it has to be moving for the needle to move. Hey, here's a generator. Why does that work? Oh, I'll spin the magnet, and now I have a constantly changing flux, because instead I'm changing the direction of the magnetic field. You can see the little compass moving. That's a changing flux too. Not changing the area, not changing the magnitude, changing the direction. Want more? Oh, let's do that first of all. There's your alternating current. Add more coils. So 1 coil of wire, I'll get 1/3 the voltage, 3 times more voltage. There you go. Or I can increase the area, also increase the voltage. You can see the electrons getting moved back and forth, back and forth, back and forth. Yep.
Increasing the area of the coil only counts if it's in the magnetic field, right? Like if it's too big to fit in the magnetic field, does it not count?
Watch. Can you see? Let me go slower. I'll go a little faster, actually. Ready? Did you see the voltmeter move? So yeah, because the magnetic field goes actually out to infinity, you can never make an area that big. I mean, there comes a point when it's close enough to zero out at a certain distance that it's meh. Okay. So, we can change the direction. However, since magnetic field is a vector, we're going to have to call one direction positive and one direction negative. Ah! Nothing. Looks like you needed that. A circular coil of 100 turns of wire, check, is exposed to a changing magnetic field as shown below. Look at the picture. What direction and what magnitude is the magnetic field initially? Look at the picture. Look at the picture. Just read magnitude and direction. How big? 7.8 Teslas. Which way? What direction and magnitude is the magnetic field after?
5.4 Teslas out of the page.
Did you say out of the page? Was the initial into the page? You're going to have to, Peter, let one of these be positive, one of these be negative. Which one? Doesn't matter. I usually let final be negative because I want to get a minus minus so I get a positive voltage. So I'm going to let this be negative and this be positive. And they want me to find the induced voltage. Well, induced voltage is equal to negative N change in flux over change in time. What's N? What's N? 100. What's the change in time? 0.12. What's the change in flux? That's what we're going to spend some time crunching. So let's see. Change in flux is going to be final minus initial. Are any of these zero? No. What's changing, the area or the magnetic field? So this is going to be B final area minus B initial area, because flux is magnetic field times area, and they're both perpendicular, so I'm good with that. What's the final magnetic field? Negative 5.4. Area, what shape?
Circle.
Pi r squared minus, what's my initial flux? Sorry, my initial magnetic field. Positive 7.8. Area, pi r squared. Please tell me, did they give me r? Oh, 10 centimeters, 0.1. So the change in flux is going to be negative 5.4 times pi times 0.1 squared minus 7.8 times pi times 0.1 squared. I get a change in flux of, do you get negative 0.4147? Yeah. And now, let's plug it into here. I got room, yay. Negative, what did we say N was? 100 turns of wire. Change in flux, negative 0.4147. Change in time, 0.12. Good to go. I get, hey, 345 346 volts. This is a good generator now. How could I get the magnetic field to change direction? Rotate the magnet. That's easy enough to do. How could I get the magnet to rotate? Hey, gasoline engine causes the camshaft and drive to rotate.
Sorry for the interruption. Grade 7s are actually leaving.
So this is Faraday's law. This is the law that takes induced voltage as BLV and extends it to, hey, this is how I can build it into something that has an area changing, spinning, hey, flux. Example 6 says, rank the top 4 loops below in order of increasing induced voltage. So go from smallest to biggest, keeping in mind that induced voltage is equal to negative N change in flux over change in time. Which of these will have the smallest induced voltage? Well, first of all of these are single loops, so Kelly, I'm going to ignore the N because it's 1 for all 4 of these. And I don't see that they've mentioned time anywhere, so I'm going to ignore that. You know what they're really asking me? Which of these has a changing, the biggest changing flux? Which of these has the smallest changing flux? Because that's going to be the smallest voltage. B, why? Okay. B is going to have an induced voltage of nothing. Yeah, it's moving around, but there's no changing flux. Which one do you think would have the next smallest change in flux? D? Squeezed a bit, so a little bit of change in flux, but not big. Which one would be next? I think C. I think A has the most voltage because A goes from full flux to no flux. I think that's the biggest change in, as opposed to C, which goes from full flux to some flux. So I think C, then I think A. It says, explain your answer. We just kind of have. Almost done. Summary. When you're talking about induced voltage for a wire, use BLV. For a coil, change in flux over change in time, except I'm missing a negative. What's your homework? First of all, finish lesson 1, but you need to practice this. Number 1, 2, 4. I skipped 3. By the way, I'm going to skip 5, but for what it's worth, helicopter blades generate a voltage because they're rotating coils of wire through the Earth's magnetic field. One of the real dangers when they're picking somebody up from the ground via a steel cable is that steel cable could actually pick up a high voltage and discharge into the person. It's something they have to be aware of, believe it or not. So, but I'm going to skip that. You know what? I am going to assign number 3 as well. So right now, 1, 2, 3. Finish off as well lesson 1. And you also can be working on your electromagnetic forces review.